In this video, we'll continue our discussion of curvature, given the formula that in our last discussion that we came up with. Curvature is the magnitude of the derivative of our tangent, unit tangent vector with respect to arc length. You could probably guess why this isn't a great formula, really, because it's the arc length thing kind of throws everything off, because I'd have to find an arc length function and plug all that. It gets way messy. So we need to come up with some nicer formula, even though that works, if I have arc length. So let me show you a manipulative to get to a better working definition, more of a practical one. Okay, so if I use the idea of a chain rule from Calc 1 here, I can introduce this arbitrary parameter t, or I guess it would really be the s there. Arc length would be our s, and then little t there. Recall that everything checks out here. We're going to do something with that equation, but I really want to think about this for a moment. Recall over here that s is our arc length. If I take ds dt, that's the definition of my arc length, the derivative of an integral, those are inverse operations, so that's going to leave me with that. And then, I don't know if you guys remember, I hope you do, the r prime of t is actually velocity. So what they did here is they took this equation and they took the absolute value in magnitude where appropriate, so we get dt. That's a vector, so magnitude makes sense. The vector of dt ds, that's also a vector, so magnitude. And then the last thing, ds dt, that's actually a number, so it's actually just absolute value. All right, but I can replace that with the magnitude of v. So this equation becomes dt dt. And we're solving for ds. Actually, we don't need to show that. We could just write this in real quick. dt ds. And then we're going to replace that with v. Now, if we were to solve for dt ds, because that's what I really don't want to deal with, I would like a better definition. If I were to divide both sides by the magnitude of v, I arrive there, here. And then we know from this definition above that it is equal to kappa, which is our curvature in this case. I'm never going to ask you to rederive that or explain it. I'm just going to have you use the working definition. All right, so let's try to find, I didn't write the directions for this, but I will write it. Consider this line, and then I will type these into your notes, but I'm going to write them here. Show that kappa is equal to 0 at all points on the line. All right, so if I were to find kappa, I'm going to need a couple things. I'm going to need a tangent unit vector, so let's go ahead and do that. A tangent unit vector, remember, is defined r prime of t over the magnitude of that same vector, making it a unit vector. Okay, so I need an r prime. So let's do that first. We'll do it down below. R prime of t is just our derivatives in each one. Derivative of that, a is just a constant, x naught is just a constant, so the derivative here would just be a. The derivative of the second thing follows the same type of logic. The derivative of that gives me a b, and then derivative of the third thing gets me a c, and I get a vector of just a, b, c. Notice that everything in that vector is constant. I need to find its magnitude as well. That is going to be the square root of a squared plus b squared plus z squared. All right, so we have both parts. So it's going to be 1 over the square root of a squared plus b squared plus c squared, right, times the vector a, b, c. Okay, so we have, that is our tangent unit vector. They want us to find, it is a unit, so they want the derivative of that thing. That's what we're trying to get now. I have t. They want the derivative now with respect to t. So derivative with respect to t, dt. Well, what is the derivative of that with respect to t? Well, it's the derivative in all three parts, which is going to be 0, because it's a constant. Derivative of the b over that is a 0, and the c is a 0. Right? Well, if that's the case, then the magnitude of dt is equal to 0, which in turn tells me that kappa is equal to 1 over magnitude of velocity times the 0. So we get 0. So kappa is 0. Notice I never plugged a point in or a t for a certain point. We just did it for, use the formula in general, and it led us to that kappa is 0. This would make sense because this is if you haven't put it together, this is a line. Right? That's a line in 3 space. The curvature on a line would be 0. It does not curve at all. All right, let's take a look at our next one. Consider the circle. We did a line. Let's look at a circle now. If you can't put this together, this r, we've been dealing with a lot of circles lately. That r is our radius. So that is our radius of our circle. Cosine is my x-coordinate, sine is my y-coordinate. Those together give me that circle with a radius r. If I do t from 0 to 2 pi, where capital R is greater than 0, that makes sense because it is the radius. They want us to show that kappa equals 1 over r. Okay, so the first thing I need if I'm building towards my derivative, my definition, is I need r prime. This is also going to serve as my vector v. All right, so this derivative is going to be negative r sine t, comma, r cosine t. That's the derivative of each one. I can also now find the magnitude of v, which is also the magnitude. We're going to use them both in 2 different definitions here in a moment. That's that same thing. Okay, I get the square root. If I square each one, I got r squared sine squared t plus r squared cosine squared t. All right, we can factor out our r squared. Sine squared t plus cosine squared t. Hopefully, bells are ringing inside of here is a 1. Right, that's gone. The square root of r squared is an absolute value of capital R, but we already said that r is greater than 0, so I don't need to put absolute value. So we have shown, okay, now that is always an r. So we're building to 2 different definitions, okay? Let's do our tangent unit vector. Tangent unit vector is equal to r prime of t divided by magnitude of r prime of t. So I have r prime, which is negative r sine t, it's from the top up there, r cosine of t, divided by its magnitude, which we just got was r. Okay, this unit tangent vector is negative sine t, cosine t. Those r's cancel. Okay, so now we have that. And we need, for our formula, we're also going to need to take its derivative, d tangent unit vector, and with respect to t. It's not a constant this time. So the derivative of negative sine is negative cosine t. And the derivative of cosine t is negative sine t. Right? And then we want in our definition, that is a magnitude. So we need to take the magnitude of that. But if we think about this, let's make sense. Let's make sure the magnitude of this would be a 1 because it's a unit vector. Let's just make sure you can kind of see it. But let's check out the magnitude there. Okay, that works out. Cosine squared t plus sine squared t. Just to check, it is 1 as well. Okay, so I'm not sure if that's safe to say always. If we think about it, I'm not sure. I'm scared to say that the magnitude of the derivative of our unit vector will always be 1. I would really maybe go explore that. Okay, so I have that as 1. Now we have our curvature definition, which is 1 over the magnitude of v times the magnitude of dt dt. Actually, it wouldn't make sense if that was always 1, then this definition wouldn't have that at all. Okay, so in this case, it ends up being 1. Okay, I got 1 over the magnitude of v, if I scroll back up, was r, 1 over r, and then that's just times 1, so I'm not going to write that. So kappa is, I'll do it for note 6 since I'm going to write it again, 1 over r. That's what they wanted us to show. This is always for a circle. This makes sense if we think about it. A circle is should have constant curvature around, right? It has the same curve. That's actually how we base things. Think about curvatures using a circle. How close is it to that, right? Using that and the discussion that we talked about earlier. So there we go. That is curvature of a line, curvature of a circle. We're going to do other curvature things throughout this lesson. A lot of these will just be following the definition. The annoying part is going to be the algebra simplifying.